Welcome back to my course Formal Methods for System Verification. In today's class, we will discuss the decision problems of propositional logic. If you recollect the last class, in last class I talked about the syntax and semantics of propositional logic. We also introduced various propositional formula, how to encode them. We also briefly introduce what is the decision problem of propositional logic, what is satisfiability problem of propositional logic or validity problem of logic, right. So, in today's class we will try to develop a decision procedure or kind of algorithm which can actually, given a formula, can decides whether the formula is satisfiable or not. Okay. So, just to recap, what is the satisfiability or validity of a propositional formula? So, satisfiability says that there exists an interpretation under which the formula is satisfiable, right. So, you can actually assign some value to the inputs, and if you evaluate the formula will become true. Okay. And the validity tells that the formula is true for all possible interpretation, right. So, what is the possible interpretation in propositional logic? If the formula has n propositional constant, then there are 2 to the power n possible values, right. So, there are 2 possible interpretation. So, the formula is true for all possible interpretation, then the formula is valid. Okay. So, consequently, I can define what is unsatisfiable, or it also say contradiction. It means the formula is not satisfiable under any interpretation. That means under all interpretation the formula is false, right. Satisfiability is for one interpretation, at least one interpretation the formula is true, then the formula is satisfiable. The unsatisfiable is for all interpretation the formula is false. Okay. So, usually the satisfiability and validity problem is dual. So, what do you mean? If the formula is valid, f is valid, it means negation of f is unsatisfiable, right. So, it is valid means what? It is true for all possible interpretation. So, that means for all interpretation this not of f is false for all possible interpretation. So, this is unsatisfiable, right. And vice versa, if f is satisfiable, that means there exists some input for which the formula is true. That means not of f is not valid, right. So, for all possible input this is not true, right. So, this is basically dual. So, once we take a decision procedure, what is the decision procedure? So, is basically you have this kind of a algorithm, you are giving a formula, right. So, it can be a SAT checking or something, SAT checker, and it will say yes or no, right. So, if the formula is satisfiable, it will say yes, and if it is not satisfiable, it will say it is not satisfiable, it will say no, right. So, once we develop this algorithm or the method or the procedure, we have to be aware of these terminologies: sound, complete, termination, right. So, this method or the algorithm must be sound. What does it mean? It means that if you give a formula, this solver, if you say yes, that means definitely the formula was true, right. So, it is actually satisfiable. That means it never accepts a false statement. So, if it say yes, the formula is definitely satisfiable, right. You can trust that method, right. And complete is what? If you give any possible formula, right. So, in propositional formula there will be infinite possible number of formulas. If you give any formulas, this algorithm can give you the correct yes no answer, whether the problem is satisfiable or not. It can give correct answer for all possible scenarios, right. All true statement it will accept it, right. So, it basically can decides for all possible scenarios. Okay. And terminates is something, this may not go infinite, right. So, it should complete the decision within finite time. So, usually we try to identify method which is sound, complete, and always terminates in finite time. So, once the method is not sound, which is not desirable, so we usually in formal methods we always try to develop a sound method. If it is not sound, then we have two scenarios. You should be aware of this scenario, what is called false positive and false negative. What is false positive? As it says that the answer is yes. So, basically the algorithm say yes, but the actual answer was no, right. So, it is basically its answer is positive, but that is false, right. So, that means it is give a wrong answer. And false negative is what? It's saying no, that means the formula is not satisfiable, say, but actually it was yes. So it give a negative answer which is false, that means it give no but which is not correct. Okay, the formula was actually true. When the method is not sound, these scenarios come. How many scenarios the method give false positive and false negative. Okay, so I hope you understand what is the decision procedure. Now we try to develop. So as I discussed in the last class, we have two ways we can do it, right? One is effectively the enumeration, where you try to check for different inputs and see whether the formula is true or false. The other one is by proof by deduction, right? So proof of enumeration is something quite obvious, you understand. Given a formula, I know the meaning of semantic of each connector, so I can actually identify for all possible inputs. I identify P and Q this part, then I identify what is the value of P and this part, and then what is the P implication, this implication, the overall formula. And then I found that for all possible input the value is true, that means this is a valid formula, right. So this is called proof of enumeration, but clearly you understand if the number of input is n, the possible number of rows here is 2 to the power n, right. So it is always kind of exponential algorithm. So we try to develop a better algorithm, right, which is basically proved by deduction. So as I mentioned in the previous class, the deduction based on certain axioms or inference rules, right. So what is that? So basically there are certain rules which is true in propositional logic, and they are very quite easy to understand them also. So we write those inference rule the form of like antecedent and consequent. So we basically write a line here. We write what is true. If something is true, then what I can conclude, right? Antecedent is something. If I assume they are true, then what I can conclude, right? What is the consequent of that? Okay. So this is how we will write the formulas, and we have here 6 rules, right? So I'll talk about each of them one by one. The first one is the conjunction rule. So let's say I have an interpretation which satisfies f and g, right? So what does it mean? It interpretation satisfy f and g. So what can I conclude that? I can definitely conclude that this interpretation also satisfies f and the interpretation also satisfies g individually, right? If you remember the AND truth table, it will be easy to understand. So the AND truth table, I will write it here 0 0 0 1 1 0 1 1, right? If say this is f, this is g, then this is f and g, right? F and g 0 0 0 1. So only when both of them is 1, then only the formula is true. Now this interpretation is nothing but some value under which the f and g is basically is true. So definitely f is also true, g is also true. Now if I does not satisfy g, so then what will happen? It is one of these 3 scenarios, right? If the interpretation does not satisfy f and g, so that means it's at least one of them is 0, right? One of them is 0. What does it mean? So either I does not satisfy f, or either it does not satisfy g. So that is the meaning of 0, right? So if you see in this cases, at least one of the value is 0, all cases, right? So this is what given by here. So if I does not satisfy f and g, it means I either does not satisfy f or it does not satisfy g, okay. Similarly, if I say the disjunction or so if I say that the interpretation satisfy f or g, it means that if at least satisfying one of them, right? And this is also you can understand 0 1 1 0 1 1. If you take the OR, it is basically 0 here, 1 1 1, right? So this is how this means. So it is, you can see that under these scenarios this is 1. So at least one of them is 1. So if the interpretation satisfy f or g, then I will say if it is satisfying f or g, I can conclude this. It is satisfying one of them at least, right? On the other hand, if I does not satisfy f or g, what does it mean? It means it's basically this scenario, right? This is the scenario. So that means I is not satisfying f and I is not satisfying f. So that's why this is 0 0, right? Or false false. I should have used true false here, but I think you understood the process, right? So I can conclude that this is the scenario because I does not satisfy fg. So they must be individually the interpretation is not satisfying neither f and g, right. It is not satisfying both. Similarly, I can take the implication. From implication I can conclude this, that if the interpretation satisfies f implies g, then it is either satisfying f not I does not satisfy f, or the implication satisfies g, right. So, if you see the truth table of implication, so here if it is f is false, I do not care, right, it will be true. This is the case where it will be false and this will be true, right. This is the kind of truth table of implication. So, now if it is satisfying f implication g, it means either it is not, right, implication does not satisfy f in this is the scenario, or this is the case, right. It is the case where basically g is I satisfies t, right. So, this is the scenario. So, because whenever f is false or the interpretation does not satisfy, this will be automatically true, and if g is I just satisfies g, then only this is going to happen, right. So, effectively this is not f or g, right. This is how you can interpret this implication. Okay. So, now if the interpretation does not satisfy f implies g, what does it mean? This is the scenario, right. That means I satisfies f and it does not satisfy g, right. So, this is the scenario. So, this is the rule, right. This is quite understood. Modus ponens I have discussed in the previous class. So, here I am saying that if the implication interpretation satisfies f and the interpretation satisfies f implication g, then what is going to I can conclude. So, it is basically I can conclude that interpretation satisfies this, right. So, it is basically saying that it is satisfying f, right. So, interpretation satisfying f. So, this is basically this is that scenario, right. I have the interpretation that is satisfying f, the interpretation satisfying this, right. So, if this is the scenario, then this must be true, right. So, that means the interpretation must satisfy g, because in this scenario it is false, right. So, this is the scenario. Okay. So, I can conclude this. Double negation is something, if the interpretation satisfies negation of f, it means the interpretation satisfies f, and the contradiction is something, if the interpretation satisfies f and not f, then it is contradiction, right. It cannot happen. If the interpretation satisfies both the formula and the negation of the formula, it cannot happen. This also I can write like this, right. The I satisfies f and I does not satisfy f, right, and then I can say this is a contradiction. Okay. So, I satisfies f and I does not satisfy f, then it is a contradiction. So, these are the rules I have, or the inference rules, right. So, I have basically 7. So, if you have these 7 interpretation rules, can I given a formula, can I check whether the formula is valid or not? So, that is the problem I am going to do. Okay. So, how do I go ahead with that? So, given a formula, suppose I want to check whether it is valid or not. Okay. So, what I will assume that, oh, there exists an interpretation under which the formula is not satisfiable. Okay. So, this is a duality principle. Then what I can say, if this is true, that means the formula is not valid, because the negation of the formula is true, right. So, formula is not satisfiable means negation of the formula is satisfiable. So, then this cannot happen, right, and if this scenario cannot happen, it means the formula is valid. Did you understand this? So, I am repeating. So, I have to show that the formula is valid or not. So, to become the formula valid, I have to show that for all interpretation the formula is true, but checking that is difficult. So, I will take the negation of the formula, right. I am saying that no, there exists an input interpretation under which the formula is not satisfiable, right. That means the negation of the formula is true. So, I try to identify that some interpretation under which the negation of the formula is true, and if that happen, then the formula cannot be valid. So, if I can identify such interpretation, then I will say the formula is not valid, and if I cannot identify such interpretation, then I will say, oh, the formula is valid, right? Makes sense? Let us say I took the same example, right, P implies Q. So, I will just probably work it out for you. So, the formula is the F, which is P and Q implies P or not Q, right. So, I assume that there exists some I such that I does not satisfy F. Okay. So, if I can identify such I, that means the formula is not valid, right. So, what I can conclude from here, because this is implication, right. So, what I saw here that this is so I does not satisfy F. So, I will apply this rule, right. So, I does not satisfy F. So, then I can say that I satisfies F and I does not satisfy G, right. So, if I use that rule here, so I can conclude here that I satisfies this is my F now, P and Q, and I does not satisfy this P or not Q, right. So, this is what I will get. Then from here what I can conclude, this is the rules of conjunction. I satisfies P and Q means I satisfies P and I satisfies Q, and this is from disjunction what I can conclude, I satisfies. So, if you go back, I does not satisfy this means I does not satisfy F and I does not satisfy G. So, what I can conclude here, so I does not satisfy P or Q, that means I does not satisfy P and I does not satisfy not Q, right. So, now I can clearly see that this is a contradiction, right. So, if I take this and this, I satisfies P and I does not satisfy P, it is a contradiction. Similarly, if I take I satisfies Q and I does not satisfy Q, then also contradiction. So, then I saw that that such I does not exist, right. So, hence the formula was valid. Okay. So, this is how it works. So, I have a detailed workout here. I also clearly mention which rule and which line from where I get the solution, right. So, I get a contradiction there. Okay. Now, here I saw that the decision, because it is always and, right. So, that is why I write like this is and. So, I start from line number 1, then I get this line number 2, then I got line number 3, then I got line number 4 and got line number 5, right, because it's always and, there is no or. But if you see certain rules like this, there is a or here. So, that means it will create a bifurcation, either this true or that true. If you see here, there is or here. So, certain rules you have bifurcation. So, it is not that always you will get a single line like this. It may happen that you have something, from here you get something, and then you have this true or this true. Then from there this is true or that true, right. This may listen to this. So, effectively if I keep applying this inference rule, because there is a bifurcation or between the conclusion, I will create a tree effectively, right. And then what I have to show that in every path I reach a contradiction, right. Every path I reach a contradiction. Every path I reach a contradiction, because what I was interested, so there exists some I under which the formula is not satisfiable, right. So, if this path may lead to contradiction, but there may be that this path leads to not contradiction, that means this is the interpretation under which the formula is not satisfiable, right. So, essentially this proof system is like that, you have to keep applying these inference rules, and it is essentially you are going to create a tree, and you have to show that in every path you get a contradiction, right. If all path close with a contradiction, then I will say this formula is valid. But if there exists a path under which the formula become, you could not reach to the contradiction, that means this is the interpretation under which the formula was not satisfiable, hence the formula is not valid. Okay. So, I have to construct this complete tree in the worst case, right. So, I will show you one example. So, this is what I have say that the approach, right. So, I will construct this overall decision tree, and then if I found that, so if I cannot apply any more rule, that means this path is finished, and if I do not reach the contradiction, if it is closed, if I reach a contradiction, then it is fine. But if some open branches, that means I cannot apply any further rule and I have not reached the contradiction, that means this is the branch through which I will get an interpretation, right. So, that is a falsifying interpretation. So, this is the overall proof approach, right. You can understand that, right. I will keep the formula, I will keep applying those inference rules, it will create a tree. Every tree I should end up having a contradiction, but if I found a path in which I do not reach a contradiction and I cannot apply any further rules, that means this is the path which is actually the interpretation I am searching for, and under which the formula is not satisfiable, and hence the formula is not valid, right. The negation of the formula is satisfiable, and hence the formula is not valid. Okay. So, I will take now the second example in which I try to show that how the branch is coming, right. So, this is the formula. Let me again work out for you. So, this is the formula. So, I assume there exists some I such that I does not satisfy F, right, or I would say I satisfy negation of the F, right. So, if there is implication here, so I can conclude here that because this is implication, so I can go back and check what is the rule of implication. So, it is create a bifurcation, right. So, this is does not satisfy F, right. So, I have to apply this rule, right. So, this rule is there is no bifurcation. So, this is conjunction, right. So, it basically saying that if I does not satisfy F implication G, it means I satisfies F and I does not satisfy G. So, I will apply this rule. So, I satisfies P or Q and I does not satisfy P and Q, right. So, this is my line number 2, right. So, this is line number 1, this is line number 2 of the proof. So, from here I create a bifurcation, right. If it does not satisfy, what will happen? So, if this is OR rule, it will basically says that if this satisfies P or Q, that means either P's interpretation satisfy P or I satisfies Q, right. This is from this. Similarly, from this, if this does not satisfy, it says that I does not satisfy P or I does not satisfy Q, right. This is what I will get from this. Now, you can see there is a bifurcation, right. So, initially I start with 1, right. So, if I construct the tree, so 1 is this line, from there I got 2 and from there I got 3. So, basically you get 2, right. Either I satisfies P or I satisfies Q, and now I can apply this rule. So, it says that I does not satisfy P or I satisfies Q. Here also I can apply the same rule. So, it will create the branch I does not satisfy P and I satisfy Q, and this I satisfies Q. So, effectively what I have done, I just write this line number 3 here, this branch is coming from this line number 3, and after that I am applying this rule, right. So, it will again create a branch. Now, you can see here P and not P, right. So, I satisfies P, I does not satisfy P. So, this is a contradiction. But if you see here Q, I satisfy Q and I does not satisfy Q, I think yeah. So, this is not satisfying Q, sorry. So, then this is also contradiction, but if you see this path, right. So, you have all the rules done, I satisfy P, I does not satisfy Q, but from there I cannot conclude this is a contradiction and I cannot apply further any rules because I have already go back to the single literals. So, this is the path under which the formula is not valid, right. So, this is the I have under which the formula is not valid. Similarly, this path will also lead to another interpretation under which the formula is not valid, okay, or the formula is not satisfiable. Hence, the formula is not valid. So, this is how the tree will construct it. So, this is what I have shown here effectively, and this is the possible branch, this or this or this or this, right. From there you can conclude. Okay. I think here, yeah. So, these are the possibilities. This is the interpretation under which where the formula is not satisfiable and hence the formula is not valid. Okay. So, I will take the last example. So, let us say I have this formula. So, from here I can say that I does not satisfy this, it means it satisfies this and it does not satisfy this, right. So, it satisfies this and it does not satisfy P implies R, right. So, from these three what I am concluding, I does not satisfy P implies means this, the I satisfy P and I satisfy does not PR, right. So, this I can conclude from this line. Similarly, from here I can conclude that I satisfies P implies Q and it satisfies Q implies R. Okay. Now, here because this is this, so from there bifurcation will come, right. So, not P or R, right. So, not P or Q. So, there will be bifurcation from here, also there will be bifurcation from here, right. So, that so from this bifurcation and if you combine these two bifurcation, you will create multiple path and I can say that all branches will lead to contradiction. Okay. So, that means even if it is creating multiple branch, in all branch leads to contradiction, hence the formula is valid. So, there is no path under which the formula is negation of the formula is true. Okay. So, this is the complete tree here. So, I does not satisfy F, from there I get this and this, right. So, this is the first part and this part. So, from here I get this is conjunction because it does not satisfy this means I satisfies P and I does not satisfy R, right. From here I get again conjunction, I satisfy P implies Q and I satisfy Q implies R. From this bifurcation come, if I satisfy P implies Q, it means I does not satisfy P or I satisfy Q. Similarly, from here I does not satisfy Q and I satisfy R, right. Now, if I club this and this, right. So, this is P interpretation does not satisfy P and I don't satisfy P. So, this is contradiction. So, then Q and not Q, right, contradiction, R not R. So, effectively there is no branch, open branch where I get I do not get contradiction, or rather I will say that all path leads to contradiction in this tree, right. So, hence the formula is valid. Okay. So, finally, what we can show that this deductive proof system that we have developed, where I have this 7 inference rules, using that I can show that proof system that I have developed now is sound and complete, right. So, I have defined the term what is sound and what is complete. So, I can prove that the deductive system that I have done, where I keep applying these rules which will create this tree, and then I try to show that all tree leads to contradiction, and if I found a path in which I could not reach a contradiction and I cannot apply the rule, and that is my falsifying interpretation. So, this system is sound and complete. What does it mean? If you give any propositional formula, I can correctly identify whether the formula is valid or not using this proof system. Okay. So, it is sound, that means if you say it is valid, it is definitely valid. If we say it is not valid, that means it is definitely not valid, and it is complete means for all scenarios this system can identify whether the formula is valid or not. Okay. But in general this problem is NP complete. Why? Because the number of path in this tree can be exponential, right. So, every time you can have a branch and then this branch can become exponential, right. And then, so effectively you can have maybe 2 to the power n possible branch in this graph, and worst case probably you have to check all branch, because in all branch you have to see whether you reach a contradiction or not. So, it will not be always 2 to the power n, right. For example, I have taken this example where it is a linear, right. So, there is only single path. In this example I have only 4 paths. In this example I have some 1, 2, 3, 4, 5 paths, right. So, effectively it is not always exponential, but in worst case it can be 2 to the power n, right. So, complete bunch, and you have to check, that means exponential number of branches, and hence the decision process of propositional logic is NP complete. Okay. But the method that we have developed here is sound and complete, right. It will effectively give you the correct answer all scenarios. Okay. So, this is all for today's class. So, we will try to develop more efficient version of this deductive proof in subsequent classes. Thank you.